And now we're going to move to our wrap up, and it's going to be Will along with James Chu. So James, can you turn on your video, and everybody else but Will, shut off your video, please? And so I've already introduced Will, but I'm going to introduce James. He's a member of the Project Production Institute's Technical Committee. He's the Chief Technical Officer for Strategic Project Solutions. He's been in leading research and development of SPS knowledge, processes, and systems to support SPS offerings since 2001. During his career, he's worked with various organizations in oil and gas, heavy industrial, civil, infrastructure, aerospace and defense, and other industries around the world, implementing project production management solutions. He earned his master's degree in civil engineering from Yonsei University in Korea, and he's got his PhD in construction engineering management from Berkeley. So I'll turn it over to you two to take it away.
All right, thanks, Gary. Thank you, Mark and Max and Will, for setting an inspiration of where the market's actually headed, as well as actually describing your journey. So what we're going to do now is actually go back to some of the original question about the industrialization, or what people are starting to call factory models. And you can actually see many of them are starting to think about from a service model to a product-led model or product-focused model. So with that, what we're going to do is now go back and say, okay, if we're going to actually apply this concept to not just industries that the speakers actually spoke about, but wider type of projects, then we actually have to think about these different 5 levers that was actually introduced sooner today, right? So there's definitely product design, process design, capacity, inventory, and variability that determined the cost, the time it takes, and the amount of cash tied up in the system, okay? Now, although these actually speakers have gone a lot down their journey, as Todd actually has pointed out, most of the people that we actually hear when they actually mention factory model or industrialization is the gravitation toward the standardization. So what we're actually here to talk about for the rest of the time here is where we actually see the gap, which is the actual process design, the capacity, and the inventory and variability. Okay. So this terminology actually was getting mentioned a lot today, the digital twin. The digital twin is a system that actually has to be able to produce the behaviors that you're trying to analyze, understand, or simulate, right? So if we're actually going to look at a production system, what does a digital twin look like? So Todd actually introduced the concept of 4 verbs, 5 levers, and 3 curves. So let's actually use that as a criteria to understand whether these things actually are allowing you to do that, the 3 curves. So is that a digital twin that allows us to understand the behavior that we just talked about? Probably not. We did try, but it wasn't successful. 3D model, is it actually a robust way to actually understand the behaviors of WIP, cycle time, and throughput? Somewhat limited. Digital twin of post-it notes on the wall, actually, no, that was actually more of an analog twin. Again, very limited way to actually understand the production system behavior. So for us, this is the nomenclature that we typically use, and we're going to actually talk about this nomenclature with using an example with Will on what we actually are looking at as a digital twin for a production system. And it actually has to have these components: an operation, routing, the queue, stock, and the capacity that allows actually these operations to take place. Okay? So the question becomes, what does an optimal factory, in quotes, look like? And the factory could be a factory that produces rebar, pipe spools, modules, right? the terminology that the industry uses, but sub-assemblies. All these things are something that's actually being produced. Even engineering documents are something that's actually being produced. So what does an actually optimal factory look like? And how do we actually do that using 5 levers? So to actually give you a little bit of more concreteness to the discussion, what we're going to do is to talk about the research projects that we're actually doing with Clark Pacific. Well, do you want to describe a little bit as to what we're looking at here?
Sure. So what you see in the top left is a 3D model rendering of a pod product that we're fabricating or looking to fabricate for an upcoming project. So it's got a concrete floor and then metal studs with drywall insulation painting. We have bathrooms and bedrooms as a part of it. So that's the left. The right side is the area within our factory that we're actually going to produce. And what you see there is the beginning stages of the mock-up process that we go through as we iterate not only our design, but also material science. And I think James will show that in another slide to illustrate how important that is. But at the bottom, you see, we're trying to understand how the design influences how we set up the factory, all within our production system while delivering with the takt time that meets our field assembly.
Okay. So thank you. So what we actually have done working together is actually taking this picture and turned it into a model. So the first step, what we're going to do is actually create a model, a map and model, and then we're going to actually simulate, analyze, and optimize what that actually looks like. And then the third step, which is to control. So the production system behaves the way we want it to behave, right? If we can't make it behave the way we want it to behave, then there's really no reason to actually do any of this stuff on the left, right? So let's actually take a look at the map and model. This is, again, using the same language that we just talked about, but again, this is just only a portion of the production system that we have. That the actual map is much larger, but this actually shows the 2 different configurations of a module that's actually going through the system that actually uses a common capacity, right? So the common capacity use actually what actually makes it interesting, because different variation of the product, if you actually had one type of product, it's a lot simpler. If you actually have multiple variety of actual products going through the system through the same capacity, simplest way to actually is to dedicate capacity, but you lose capacity that way, right? So the question is, how do you actually optimize both at the same time? And then the secondary one is to actually simulate, analyze. So what we've done is taken that model and working with the team, are taking their actual numbers that they measured, as well as some of the assumed numbers, and actually simulating and optimizing what that production system looks like. Okay. So again, actually looking at this 5 levers. So one of the things that's actually really interesting, and I think Will just alluded to it, is the relationship between the actual process designs and then the product design. Well, do you want to actually talk a little bit about what we're seeing on the picture on the left?
Yeah, so one of the subsets of our design is how do we develop a wall system that meets sound barrier considerations within the project we're doing. So that's one of the top considerations from the owner. And so we mocked up 8 different versions of it using double drywall, single drywall, specialized metal studs, that's going through R&D right now. So it was our ability to say, here are 8 different variations, establish a cost for both labor and material, and also a level of risk and complexity along with each one of these. So we understand, as we feed this design to our production system, we understand the overall cost. We also understand the variability as it's plugged in when we start mass production.
Can you also talk about the supply chain implications?
Sure. So one of the great pictures that floated around internally was a picture of Home Depot, which is a big box retailer for us for building supplies, their entire drywall inventory at any given point in their store was equivalent of 2 days worth of our production. And so the delivery model for the standard construction materials requires a different supply chain than traditional construction. And so we're working through how do we develop the supply chain in a way where we're not telling a supplier, hey, I need 200,000 square feet of drywall at one time. I need 20,000 square feet a day for 14 months. And so it's a different delivery model. And there's a lot of time and energy and resources investing into the supply chain to understand how we develop those relationships with our supply base.
And also, if I'm not mistaken, one of the product configuration actually had certain components that you must procure from external source, whereas one configuration you were able to actually produce in-house and pre-punch all the holes to make the operation go a lot faster, correct?
That's correct.
Okay. Yeah, so those, as you can actually see, not only is the product actually determining the process, but vice versa, that they're requiring different operations, different equipment, and different tooling needs. Okay, so that's just one picture of how those two components actually levers actually mutually work together. Okay, and then the next one that we look at is once we actually have the information about the process, the rate on which each operation can be done, the amount of capacity, labor, equipment, and space that's available is put into the model, then we can start to see what is the right level of WIP we need to actually have in the system. And as many of our speakers actually have alluded to, work in process is the leading indicator for throughput as well as the cycle time, right? So if you actually increase the work in process unnecessarily, the chances, well, the physics actually says, operation science says your cycle time is going to increase, which means more money tied up and potential risk of actually missing your milestone dates. If you go too low on your WIP, then you're actually going to be missing your milestone dates because you can't produce enough. So understanding how much you need to actually have in the system is one of the things that Clark Pacific is figuring out. And on the right is understanding what the capacity utilization actually is for the current design. And actually, so there's actually multiple iterations going on. And what's interesting is one of the things that we actually preliminarily found right now is the tile, and the response from Eugene, one of your actually people that is actually looking at the product, said maybe we just get rid of the tile itself. So eliminate the operation as a whole, right? That's actually one option. But if that's not the case, then based on these questions, we're actually looking at different alternatives. So number one, can we meet the demand? Demand is what's actually set by the schedule of the client. Is the cash flow, work in process, and cycle time acceptable? Or do we want to actually try to actually shoot for a lower amount of cash tied up in the system? And third, one of the most important factors actually for the production system are the bottlenecks where we want them to be, right? So anyone that's actually been involved with optimizing a production system can tell you that there will always be the bottleneck. The question is it where you want them to be? So one of the things, if the bottleneck is where you want them to be, but you actually want to go improve the capacity, or it's not where you want it to be and you want to actually move to a different location rather than actually just adding people, which increases the cost, Clark Pacific is looking at different means actually of achieving that, right? It could be chemistry, structural engineering, mechanical engineering, electrical engineering, kinesiology, construction technology, material engineering. And what we actually have is a couple of pictures that tells us how they're actually solving some of these issues or opportunities, if you would. We'll do actually, talk a little bit about this.
Yeah, so one of the components we're looking at is tape and texture drywall. And so as you see in the right-hand side picture, you see six different variants of our ability to deliver fast enough. So when you look at the production system, like James had highlighted before, we're trying to understand how do we change the game in terms of material science. And so if precast for us is the same thing, where we require overnight strengths that are different from the traditional industry where you're pouring concrete at the job site. Same here. We require a much faster dry and set time for our materials, so we can understand our process times and meet the tack time and not have a work in progress that exceeds our physical capacity as a plant. So we're investing a lot of time in understanding what materials are out there, what new materials from a supplier standpoint are coming out that we can test in order to iterate, understand our process times, and select a supply base that works and fits within our system. The picture on the left is another example where the studs get drilled into the actual precast concrete. And so you may look at that and say, well, we should have designated holes set in the precast concrete so we can just match the walls and drill it in. But when you talk to somebody who's actually doing the work, the ability and tolerances throughout the entire system to create that wall may not line up perfectly, but it still may be within tolerance of the overall scope of the wall and precast connection. And so by developing a system where you actually can screw into the precast rather than have a hole we have to align to with a fastener allows us to be much faster and higher quality because we're not spending time focused on trying to align that fastener in the perfect spot.
Okay. Thank you. So as you can actually see how a lot of different factors are actually coming into play to actually optimize the overall production system so that it's actually minimizing the amount of cash tied up in the system. It's the production system is being designed to minimize the amount of cash tied up in the system and by actually minimizing work in process and ensuring the right capacity is actually allocated to the right place. So the next step is to actually, again, as we talked about, is to ensure that the production system behaves the way we want it to behave, okay? So to actually demonstrate that, what does it actually mean to actually have it controlled? It's to actually have, how do we actually have pots that we need at the right time and not the ones that we don't need, right? And it's not just actually talking about the delivery, but it's also about making, right? And then if we actually go further back, maybe it's actually about engineering as well. Okay? In order to do that, it's not just about optimizing how we make something, but it's about how do we synchronize. To synchronize the actual installation with the actual supply flow that we just actually looked at. So that actually has to come into play. Otherwise, we might end up creating stuff that efficiently to actually have cash tied up at these stock points between delivery and installation, right? So as Todd actually had talked about as an example in the previous session, is someone actually spent optimizing how they actually drill wells, and then that actually had increased amount of cash inventory that actually sat here, for example, and had tied up a bunch of cash that they didn't actually need to do so. Again, so what we have to do is make sure that the left and the right side actually is synchronized. So to do that, the vision is, so you actually have the installation demand that actually has the specific modules that are actually attached that provides the prioritized fabrication demand that signals the production system to produce what they need so that they can actually deliver and actually have it installed. All of this actually working in sync, right? So if there's actually something that's actually speeding up, you can take advantage of it. If something actually is slowing down, we're not creating unnecessary weight in the system. So we want to be able to create a to control an agile production system that doesn't have WIP blow up or WIP deterioration. Okay. And then start actually measuring things that are production control related analytics. So things like throughput, cycle time, WIP, and looking at all lines of balances of the activities that are actually occurring, right? Rather than a typical project management metrics that might be percent complete, CPI, cost performance index, and schedule performance index. So if you're actually managing a production system and you want to actually understand what actions you need to take, then what you want to be actually looking for is the actual metrics that's associated with production control. So once you actually have that, what it does is it allows you to actually provide data capture and input back into the model, so that this actually becomes a system that's actually improved, that allows you actually to continuously improve, right? And some of the things I think that we're discussing is, if you can actually automate a lot of these things, then again, I think we're actually a step closer to what we talked about is intelligent production, where it's a self-optimizing system. Okay. So one of the things that we actually seen, and I think Todd actually brought it up a little bit earlier, is I think you actually have a choice. You can actually take the approach of a trial and error, right? And I think we actually see a lot of that actually in the industry. And when we actually watch the trial and error, they say, well, we're actually doing continuous improvement. But if there is a way to figure out and design something and then control to it, why even do a trial and error? Because you actually have a good basis to start with. Okay? So whether you take the trial and error approach when you actually are adopting industrialization or design and control approach, I believe the choice is yours. Okay. Okay, that's all we actually had, and I think we actually have a few minutes for questions.
Yes, we do. Thank you. So we're looking for some questions from the audience here. We've got about 7 minutes, so please feel free to light them up here. Maybe I'll get the ball rolling. So how long are you into this process of getting your lines of balance worked out and optimizing the system?
Well, so we're a couple weeks into understanding our process and finding a lot of these interesting data points that James highlighted. I think we're 8 or 9 months out from mass production. So we're in a place where you saw those 8 pictures of the wall systems. We're actually using that mock-up to change our design in real time. And so I think it's one of those things in the construction engineering industry where, a lot of times it's why I got to get it 100% before we actually test it. And we're changing that model by saying, give me the 8 different versions of what you want to do, and we'll test all of them, and then we'll provide the options and the feedback. So we call them one-way doors. We don't walk through a one-way door and put ourselves in a bad spot and then have to live with it over the course of the 14-month production cycle.
Yeah. So we're starting to get some great questions here. This all sounds logical. What's the biggest mindset bottleneck you found with your colleagues?
So, so I'm coming from the world of consumer electronics. So my mindset was high volume. We did 10,000 prototypes before we went into mass production, tweaked everything, changed every design to delight our customers. And Clark Pacific's, the journey that I talked about was very much an engineering company that got thrust into the 2000s with large-scale projects that had to make, that made engineers have to think like manufacturers. And I would say we're still in that journey of understanding how do we as a company create a collective mindset, bring in people who have a different view of what production, manufacturing, operations looks like, inject that in a positive way, and move forward. And I think that this product that we're working at has all those elements, right? There's a design element, there's a delivery element, there's a manufacturing element, there's an R&D element, and it's forcing that team integration that I talked about, which is very unique for us because it used to be engineering delivers to manufacturing, manufacturing delivers to the field. Now it's a loop of cross-functional teams that are delivering it together.
And you're in this process of converting from a push approach to an entirely pull approach. That's a big shift. And along with that, another great question. James mentioned using lines of balance scheduling for his analysis. LOB is such a powerful tool. In your experience, why do you think LOB is not used more often by U.S.-based construction companies?
Oh, that's a great question, and thank you for asking that. Number one, I think what we're actually doing is not using line of balance to schedule, and I think some people are trying to actually do that. What we're actually doing is observing the line of balance as an output to understand whether there is a discrepancy between the actual rate that we're actually getting from the model rate that we are actually planning for. Okay, so that's what we're actually trying to understand. That's what we're actually using. Line of balance scheduling, again, is, as you said, it's not something that's actually a lot of US companies use, but what we're actually doing here is understanding the rate of what's actually being done using line of balance.
Sure. And so why aren't more people using it? It's powerful.
As a depiction of what you're actually getting, it's a great, powerful tool. The only challenge is, number one, you need to actually have your production system defined in order to be able to map that, right? And if you don't actually have your production system mapped, then I think people typically actually have an S-curve, and those two, they believe that they're synonymous.
I think you're spot on. Traditional project controls don't provide you any of that information, don't provide you any flow information, and only provide you earned value information. So it's just an apple and an orange. And I think the historical practice is project controls, not production management. And so that's the shift we're trying to make, huh? But when you see it, it's pretty compelling. So maybe seeing is believing, and hopefully we got a few more believers here after participating today.
And what's interesting, I think Martin actually asked about the mind shift. And that's actually one thing to actually talk about. It's always actually interesting to work closely with the people that are actually trying to implement this type of an approach and challenge. Because when we actually are looking at different alternatives, we're actually looking for some data, the return and the feedback loop cycle is probably within hours.
Yeah.
Right. And when we actually had to introduce this concept, we actually had, we should say, all of your top management actually in one room, spending whole day going through the basics of the operations science that they actually wanted to get around the common language. And it actually involved two CEOs actually sitting there for a whole day. And so that's actually that was like pretty interesting. It tells us that they're really trying to do something.
I want to thank everybody again for all your insight, sharing so freely and talking candidly. And we're going to close this segment off